Welcome to the Generation AI podcast, where we demystify artificial intelligence in the world, the amazing world of higher education. I am JC Bonilla, joined by the insightful, amazing, and now in the groove of back to school, Ardis Kadiu. How you doing, buddy?
Hey, JC. Welcome back stateside. It's good to see you without a crappy internet connection.
No more hotspots. The internet connectivity and broadband access has basically been modernized because, for the past month, I've been relying on good old DSL connections. But here we are, back to school. My kids started yesterday. New York City State's public system started yesterday, and fun. Basically, kind of have that routine, and you kind of know a little bit how your day starts. Less in daddy camp, more in human JC mode, but all good. What about you? Anything exciting? Your kids have been in school for quite some time, so you're not there. But schools, most of them are kind of full 100% this week, so you're probably feeling it on the element side, right?
We are, yeah. We're getting a lot of folks are working on their new season or their new recruiting season. They're getting their applications live. They're getting their communication flows. We're getting a lot of questions around that and best practices. Events are in full swing. So yes, we're definitely feeling it for sure from the element side. It's been interesting because, fall usually is that time where you get school vibes, right? It's like even though you're not in school, like the temperature outside cools down. You get the fall feeling, the back to school. You just get a very different, like, I want to learn something new. I want to go to class. Or of course, you're teaching as well. Are you teaching this semester?
Applied data science for process improvement, right? So, which is a version of my business analytics course that has morphed and adapted to industrial engineers. So yes, good old central tendency being uncovered this week, moving into central variation next week, and we built towards predictive modeling at the end. So if you choose to be part of this exciting course, hit me up or registered at nyu.edu. Actually, you have to apply for a whole master's. It's quite complicated. Ardis, what are you the most excited about this fall in terms of you, the lead there, right? So there's a ton of travel. You told us schools are busy. There's a million gazillion things that you're building on Element. The one thing that you look forward to, and it could be AI or not AI related for the fall.
We did two episode series with Petter and I a couple episodes back around the idea of AI agents and AI agents or proactive agents. This notion of agents has been really on our minds quite a bit, and how we're thinking about it in Element. And we're starting to implement those at Element. And it opens up a lot of possibilities. And one of the things that's really exciting about these agents is that we move away from the idea of AI kind of one-shot prompting to maybe some things happening in the background, to now moving to a place where AI can put multiple tasks together and can get things done a lot faster, a lot easier. And that's really, really exciting for me. So I'm talking to a bunch of different conferences around it, but also we're building it live on Element this fall. So starting to think through, and then the world of AI, or like those folks who are building AI right now, we're seeing a lot more of that content happening. So this is very exciting for us because there's two parts to it. One of them is technologically exciting, but also it's exciting because it solves a lot of the problems in higher education, in CRM, in outreach, in communication that we care a lot about. It's like that idea of the next thing, like what do we do next, and how do you keep track of this notion? So that's really exciting for me. And I think part of that today, we're going to talk a little bit about this idea of reasoning, right? It's like, how do you figure out what is next, and how do you break things down? How do you break those tasks down? But I'll let you drive this. This is going to be your episodes, and we've kind of transitioned into it all together now. So we're now in the episode.
Thank you. Yes, when it comes to reasoning, you can trust me. Do not trust Ardis when it comes to reasoning. He's a very unreasonable human. Everybody, yep. Today we want to give you this idea that reasoning, AI reasoning matters. And more importantly, we want to open up the curtain of what AI reasoning is, current trends, and where is it going. Why? Two things. Number one of the important aspects that we are starting to see in the trends of AI is that the whole LLM conversation, the technology stack and empowerment, the machinery of AI is starting to lose a bit of the, I guess, conversation, and now we take it for granted and it becomes an application. So it's always important to understand the fundamental of reasoning. How are systems, specifically AI systems, learning, making decisions, and specifically approaching solving problem. So this episode is specifically about the components in machine learning and AI and expert systems that allows us to basically go through the complexity, through the from input to output, right? So, and we'll start the episode with three important things as we are going to be using them: knowledge representation, reasoning algorithms, and the learning algorithms. All these three are in a way combined similar artists. So imagine when we think about AI, machine learning, or advanced analytics, we're talking about the same type of variation of using data to predict and forecast where things are going. So very similar. Knowledge representation, reasoning algorithms, and learning algorithms are similar. However, think about knowledge as storing and manipulating the data. Gigantic applications there. Two, reasoning is how do I draw conclusions? And three, in terms of learning, how do we improve performance over time? And AI reasoning and complexity of these AI systems kind of has this feedback loop. Does that make sense as we kick off the conversation, Ardis?
Yeah, no, that sounds great, JC. So how does this fall into, can we also touch base on the idea of this large language models and how they reason about giving us those answers?
Yeah, like everything we know, there's an aspect of trying to understand how you and I go through reasonings and mimic that through computer programming, right? In computer systems. So the first one, it's what we, in research methods, we've been talking, and you probably have heard about this, deductive reasoning. We need to teach algorithms to derive conclusions from a generalized principle. The apple is falling from the tree. There's something called gravity, right? Versus inductive reasoning, right? So you start generalizing from observations or cases to make a broader conclusion. I see an apple on the floor. I see a pear on the floor. There must be something that is causing these fruits basically to fall down. And then you end up with the same kind of generalization that there's a principle of gravity that makes objects fall, right? And this is something that all of us in a way should be familiar with, right? Deductive versus inductive reasoning. And computational power, LLMs and whatnot, need to be trained to do that. And we're going to talk a little bit about how that happens. But two really important, in a way difficult and exciting ways of reasoning, which makes AI reasoning the framework of reality, is abductive and common sense reasoning. So what is abductive? You infer, right? You make an inference, you make a decision, you make basically a call of knowledge from the explanation of a set of observations. So in a way, I'm not observing the fruit falling. It's just that I read in a book that all these things have fallen out of a tree, and all of a sudden I can make an inference. But it's that explanation was given to me. Common sense, which is very, very human, is this idea that now I'm using intuition, right? So I see a bunch of apples in a basket. There's a tree in front of me. Something must have happened, right, for those apples to be from the tree onto the basket. And I could make the connections that they maybe fell or someone picked them or whatever. But that's basically what a computer system needs to do. Deductive, from conclusions to the principle. Inductive, the observations generalize the principle. Abductive, it is shown in a way. And then common sense. Questions, Ardis? Does that make sense?
Yeah, no, that makes sense. So as I think about this, for the AI systems or the LLMs that we're dealing with today, basically what we're saying, their LLMs are really, really good at making connections. So
That's what they thrive, right?
different, right, exactly. That's what we're really good at. Like, how do you put different ideas in different, completely different fields? How do you pull from that knowledge to come up with like a synthesis of these components, right? Which is really, really interesting.
And the speed in which it explains, right? Because I can make the conclusion of a basket tree and then like generalize how it took place.
Right.
It's just that an LLM would do it in a nanosecond, right? Whereas me, I'll probably take me a few rounds and inspirations and maybe some additional enhancers of inspiration, if you will.
So that's the last part. Now, on the beginning part of it, LLMs are not very good at following rules, right? If you tell them like, "Hey, what's 2 plus 2?" Like, even though they have learned a lot of math or they have seen a lot of those examples, they might not know the rules. So, like this rule-based world that we have right now, we as humans can derive those rules and can say, "Oh, we follow this step and this step and this step and this step," and then we derive the answer based on this step. So this idea of chaining together thoughts and chaining kind of rules together, that's something that is not available today in the large language models.
But that is the reason why this is such an important topic. 2 plus 2 equals 6. Like, what the hell happened? I know the answer is 4, but the LLM is giving me 6. So
Right.
basically, the quest for explainability. How did the LLM arrive to that solution? How can I trust that? And there's safety in the answer. And obviously, 2 plus 2, it's 4. It gives me 6. There's not that much complicated things. But what if we're talking about cancer treatment in a man who's 85? Should I give you a doses, right? Should I give you some type of solution? The ethical considerations that AI needs to make in terms of reasoning are severe. So why do we care about reasoning and the transparency and the trust and the ethical considerations? Is because all these are at play. And we can go from 2 plus 2 to, should I unleash a medical solution, diagnosis, or treatment to someone who is in need, right? And ultimately, this is all anchored onto improving performance, right? Because I'm going to take you back to my engineering years. I something it is so analog and digital, right? But something that caught my eye when I was working in semiconductors, artists, is that performance and testing is what makes the chips very expensive. So let me explain. When I was working at Intel, a chip was like $30 in production, but when it got sold, it was like $300. And now it was not the markup in brand from Intel. It was literally the testing and the basically what is called functional and structural testing that allows the chip to say it's going to last. So all these things that we're talking about, in a way, are computationally tolling. They're basically pushing the algo to do additional things and improving performance, and it will cost money. So how much more we want to pay to obtain the explainability, the trust, and the ethical considerations in AI that are must needed, right? So that kind of, in a way, anchors why is an important thing, and we can now start talking about the trends. Anything for you to add, artists, and why is it important, what it is?
Yeah, I mean the importance is because as we are going towards what you call in here common sense reasoning, right? And for some of us, we would say, okay, like these are AGI or artificial general intelligence would be the equivalent of these fourth level that you have in here, which we call common sense reasoning. When you see a new problem that you haven't encountered before, and you're making decisions based on that, on how to solve that problem, or you're seeing a novel problem or whatever it is, and you're making decisions based on some knowledge that you have, or you're reasoning about it and solving that problem, right? So the capability of these models or these AIs to solve problems that they haven't seen before, that's where we're going. So that's why this is really, really important, and why we should care about this is because it's not just reasoning for ethics and explainability, which is very, very important, because we know these systems are opaque to us, but now we can kind of ask them why did you come up with this solution, or why did you do that? But it's also about the capability part of it. It's like, we need to have training data. We need to tell them how to reason about or how to approach problems in order to get to that AGI component that is going to be maybe a few years away.
In art, is an important distinction of the three things that we're going to talk about in trends is that this is not AGI, this is not even generative AI. This is literally the current state of affairs, the state of the art in research, if you will, for good AI, right? As it relates to reasoning. And of course, the future trends and how we're going to end up moves more towards generative AI and basically...
I'm getting ahead of myself.
No,
I'm getting ahead of myself.
No. It's just what I want everyone to understand is that these three things that we're going to be talking about next are basically how AI researchers are thinking about opening up the transparency and the explainability, the trust, and the performance that is needed for the next wave of AI that we've been talking about to basically be attainable. And number one, Ardis, it's called explainable AI. Number two, neurosymbolic. And three, human AI collaboration. One disclaimer or a mental model that I want everyone to understand. Think you're an economics professional, right? And many of you who listen to us understand this kind of idea of econometrics or ratios. You are an expert on predictions using regression models, right? But you never worked with, classifiers. So all of a sudden what you have is techniques or bodies of work that will tell you, I'm going to be specializing on explainable AI, XAI, or neurosymbolics, or human AI collaborations. You start seeing, I'm not a regression modeler person. I'm a time series person. I'm all about forecasting, but I work more on, forecasting and supply chain. What I'm calling out here is that this body work is going to be so important that I foresee data scientists, machine learning experts, and AI experts to have a specialization on any of these three. So what are they? Explainable AI. Very simple. It refers to the methods, the techniques for making an AI system transparent and understandable by us humans. Let me give you an example, okay? And this example has a beautiful narrative in parallel to all of us in admissions, right? So I'm in a bank, and what happens in a bank? I ask for a loan. So the input is the applicant's data. It goes into a black box of yay, nay, and the output is loan denied. Sorry. By the way, it feels like it is today, right? So
yes.
What is explainable AI? So think about a model that does the following. Applicant, data, input, a layer of explainable AI, not the black box, the output is loan denied. Why? Because it would come and say, principal factor for denial is that you have a low credit score. Specifically, 40% of the weight comes from credit score, and you're basically below. And the second factor is that we're looking at the ratio of employment history and late payments, and that's about 10% of the weight, and then you're basically a little bit low. The fact that we can able to ping and interpret and get that specificity for a model, it's super hard. Ardis, how many ML models are running an element and you're able to basically ping them at this level? Is this something that is attainable, right?
It's not. Well, I was going to ask you, it's like, well, this is a very simple example with just a couple of variables or a couple of factors. But what if you have hundreds or thousands, or in the large language model, like you have billions of parameters that you're tweaking? How do you explain that?
Well, and it's basically what we're trying to reach through here is the aspect of transparency, right? That if a decision is being made, if a decision is binary, yes or no, denied, not denied, approved, not approved, a car left and right, we can come back and understand the transparency that if the decision was right, what are the factors contributing? And to your point, it was not a factor. It was 1,585 factors, right? And all of them were processed at once. But at least knowing that and have the ability of that. Why? Because it goes into fairness. Ardis, think about it. I need to improve my admissibility. I need to improve my, accident rates. Why are the goddamn cars turning left? Why am I denying all these good-looking Latinos who are bald and have no hair? So that is some of the things that are really important because many of these algorithms are just giving you the outcome, the output, without us, the experts or the leaders, with a layer of interpretability and why that happens.
So like if I compare this, for example, with like the generative AI with our chatbots and ChatGPT or Claude, or large language models, one of the techniques that we tend to use to get better results at the end is saying, go step by step, right? We tell the LLM to go step by step, and it kind of produces better results at the end. I don't think we're quite there in terms of the reasoning or what you're talking about, the explainability, but there's just something, about explaining, that it makes the end result feel much more concrete because you're following all the steps through and you're kind of explaining things a little bit better.
And then let me take this to the next level. Think about the field of explainability, right? Explainability AI, XAI. As number one, it will be regulated. So if you need to go step by step, or you need to start making sequential type of training, whatever, because FAFSA or the federal government is regulating every admissions, and this decisioning using algorithms as it relates to financial aid will be regulated. So all of a sudden, you have to expose that. Why are you giving more money to Susie versus Mary, right? Number two,
Yeah.
model improvement, right? We're getting stuck in this loop. The sequential aspect versus the parallel aspect are different or much better. A lot of model improvement and how it gets refined can be found on explanations. And there's two ways in which we start thinking about it. You could be model specific. I need to make this transformer. I need to make this specific GVM or whatever models you use better and faster. Or you could be model agnostic. And there's these techniques called Lyman Shop that are excellent at basically giving you explainability when you have deep neural nets, which it's thousands of parameters with the other complication of layers. So you don't even know which parameters and where is happening, right? But Ardis, regulation, model improvement, also visualization tools, or some important aspects of interpretability is that it's interpretative and interactive. So what charts, what visuals do I give you? Just like the output needs to be visualized, we need to start thinking about how do we convey explainability as a product. So plots and action maps and features and kind of like what decision trees used to look back in the day, that you can see a decision tree was very graphical, but when you have ensembles, 500 of them, it's super hard to do it. A bit of that. And potentially, right, this is kind of how the trade-offs between accuracy, interpretability, consistency, fairness, all of it comes together and shapes the field of explainability in AI. How's that? You're nodding?
I'm nodding because we're kind of marrying two things together. When people think about this reasoning and explainability in AI, like all of these areas of study, just like AI has been around for a really long time, and these topics and these questions are not new. But what we hear today in mainstream, let's say, knowledge on AI, it's around generative AI and these large language models. So I really, really appreciate you bringing it back to, hey, these things have been around for a really long time, or this kind of fields of study in AI and systems that are complex systems. So now how do we map that into large language models that are much more capable and that are, potentially much more, important? Like we need them to tell us how they got to those answers, introspecting truth, introspecting the ability for us to understand like what they have learned, what they're capable of, safety, right? As they get bigger and bigger, we don't even know the latent capabilities that they have. So now the fields of research that are going into safety in these models, like we need to be able to know how to query them and how to get them to tell us, what their capabilities are, right? So it's really, really fascinating, this whole world. And thanks for kind of breaking it down into those three different areas.
So keep in mind that explainable AI as the field, right? It's kind of the model level. It's trying to make a specific model, a SVM interpretable. There's a discipline called neurosymbolic, and it's two components. Specifically, it looks at type of models that are neural components. So think about a convoluted neural net. Everything that happens with LLMs kind of have this idea of inputs, layers, and output.
Right.
And symbolic. What is symbolic? Think about decision trees or a layer of if A, apply B. So the best way to do this is through an example. So we're going to go to the doctor, and we have a system that uses neurosymbolic reasoning for AI. So first, it's going to go through computer imaging, and it's going to be detecting using a convoluted neural network, that all these X-rays basically could have dark spots, could have these things, and that's what they mean. It's trained to basically give a diagnosis out of an X-ray, and it's trained basically on a dark spot means cancer or not, right? Type of things. You with me? Second component.
Yep.
It's basically, well, if you have long, dark spot, which is basically could be cancerous, and fever, then consider that as a sickness. I can never pronounce pneumonia. Is that what you call it? Pneumonia?
Pneumonia, yes.
You have this darkness, you have fever. So that basically means your course of action should be, pneumonia type of treatment. But if there's no fever, in this case, that's a symbolic map. That's the heuristics and decision rules. You should go through a different track. Specifically, do you have smoking history? And if yes, my friend, you're moving into the track for lung cancer screening. And that's basically how two type of reasoning systems come in place. One is 1960s kind of decision trees. The other one, full neural nets using computer imaging, right? And that's basically what is called neurosymbolic learning. And it's about the integration of these kind of thinkings of components of AI. Make sense?
That makes sense, yes.
So here, all deep learning, which is basically more modern type of deployment of AI, is eligible for. And think about any type of logic-based system that would benefit from, it would come and make it a reality. It's really exciting because one of the things that I like about these artists is that it allows domain-specific expertise. Oh my gosh. Do never do this with this type of student. Do never do this with this type of brand. Do never do that with this type of product. These are things that we know just because we know, right? As professionals, we've been doing it for 20 years or 30 years. So you don't need to have the machinery of LLMs to replicate what is known. And that's one of the things that I really like about this type of reasoning in AI.
JC, can we double click on that just a little bit more? Because I feel like this is some of the discussions that are happening right now in the field, and some of the excitement that's happening around the newer reasoning models like Strawberry, for example, that OpenAI is introducing. This notion of how do you encode the rules into an LLM? Like, we know the rules, but we can't really encode them because it only learns for data that has seen or examples or whatever. But these rules are things that we as humans have picked up differently, but they're not codified anywhere. They're not in any materials. They're not in anything. There is no remember, like we do SOPs or, like in organizations, we start thinking, okay, in order to get to this outcome, this is the reasoning and this is how all the things that you need to follow. We have very little of that data. Like, it's like show me your work type of data, right? In order to learn from the rules on how those things are done. I think that's at the crux of a lot of the reasoning research that's happening around models now is how can we embed that capability to these models? How do we do that when we just don't have data to feed it that way?
And this is basically going to be a fantastic connection to our next episode on synthetic data that allows us to basically say, I have not seen that data, or to label this data is going to cost me millions of dollars or, 14 weeks of work. So how can I use the current machinery available today to generate the data so I can train against that, right? And we can talk about the good and bad of that approach, artists. The last one is such a powerful, interesting, and I'm so bullish about what human AI collaboration looks like, because as you hear about it, it could be like, oh yeah, it's obvious. But as a discipline, it's very interesting to understand when do we allow the algorithm to lead and when do we wait for the algo to get human input to kind of keep on going in that sequence of input to output. And human AI collaboration refers to a system where humans and the algorithms, right, AI, work together to achieve a common goal, right?
Human in the loop.
Human in the loop. And the applications are fascinating and endless. We think about the AI as a coworker, right? And how experts and researchers are trying to think, how do I insert the perfect human in the loop, knowing that it's hard, like, of course, I need the human to tell me, or I need the AI to tell me. It's a hard thing, right? And the feedback loops and the ethical and trust considerations, as you can imagine, incredible trends. And we see this across the science sectors, creative industries, healthcare, finance, and many other places.
Yeah, I mean, we're building this AI as coworker or AI assistants, so to speak, right?
Ardis, with that in mind, where do you find Element steering towards to, right? And I know you're not a research shop, so you're obviously more on the practitioner and expert side here, but are you more on the basically human AI collaboration type of reasoning? Are you more on these neurosymbolic systems or more on the explainability? Where do you see Element playing, spending more time in its use of AI?
We want to do a lot of things autonomously, so proactively, right? So, because one of the things that top of me for reasoning purposes is this idea of right now I can ask ChatGPT or I can ask this large language model something, but they're not able to reason through what are the things that we need to do in order to produce the next best action for the student. There's a lot of rules, there's a lot of kind of what we call playbooks, or there's a lot of learned actions that as professionals in either marketing or recruitment or student success, like we have these learned things that we take a whole bunch of data and then we say, okay, what's the next best thing that we can do? And we have a set of rules that we follow or a set of heuristics or whatever it is. So we reason through the data that we get and we say if this then that, but we do that really fast in our heads. And then we're like, all right, most likely we need to reach out to the student and or call their parent or do whatever. So we can't really ask an LLM to decide what's the best next thing because they just haven't seen data for admissions or haven't seen enough marketing data, system data in order to say, okay, if I have all these different things together, what do I do next, right? So what we can do is we can do perhaps some fine tuning or we can bake in the reasoning steps and say, if I send them an email today and I send them a text message tomorrow and I do this step and I do this step, what is the most likely thing I should do if I have the context of this person, but I did all these different steps before? Can I reason through what's the most likely thing to do next? And if I reason 2-3 steps ahead, then I can reflect on myself and say, is that really good or is that really bad? So the reasoning part that we're working on is around building playbooks. Think about these as kind of frameworks of reasoning. And because the LLM or the system would come in and say, this is why, like it explains, right? This is why I'm thinking about doing this step, right? So it's doing an action and it's giving you the reason for doing that action. Now you have another data point. So imagine you have all of the reasonings, all of the different data points for every single interaction that this AI assistance has done in order to get that student to a particular goal. And those all of those pieces and all the interaction, now that data goes back into it and it can reason even better on the next one. It says, oh, I understand because you did this and you did this, and here's the reasoning parts, and here's the step by step, and it's really, really good at giving me a better answer if I go step by step by step. So that's what we're building on right now, but we're not researchers, right? But intuitively, we know that we have to encode that, that secret sauce. That's really our secret sauce at the end of the day. It's like, how do you bake these playbooks into our system so we can get really, really good outcomes, at the end? And we used to do it with things like packs or like automatic campaigns, and now we build campaign builders, but they're still not to the point where I can do an automated, like the best and next action, right? We haven't figured that out yet, and that's what we're working on right now.
It's fascinating to hear you go through these motions because it's very clear to me that as an expert pushing and applying the technology, you're pushing the AI reasoning in two specific ways. What is basically the algo and the rules, the symbolic maps come in place, so the neurosymbolic. Specifically, what I can know in your product, I think what happens is that we're going to do this, but for your school, you want to apply this layer of decisions. For other school, these are all layers, and you got to figure out what to bring it together. But there's the second part, which is you're trying to play around with the human AI collaborative aspect of reasoning of, we just don't know if this is the right thing for you. So we're going to make a decision, and then is the right one, and creating that feedback loop of moving forward makes the right decision, and approximating the LLM or the AI to the trueness of what is next for that student journey for that particular school. So I think that's really what happens in your journey, which is fascinating because you're pushing at least two of the reasoning areas to the next level.
Right, exactly. So coming up with that synthetic data or those data points that we can fine tune these models, that we can say, hey, you've seen thousands of these journeys or thousands of these examples, and here is the reasoning behind each individual step. Now you're really fine tuned to make, like, given 20 data points or 20 kind of steps in the journey, predict the 11th step, which is models are really, really good at. Correct. Right? But generally, where models are going next with OpenAI and Strawberry is that they don't have that innate capability of reasoning. They can't reason right now. They're basically like aggregating, and they're predicting the next token. So because they haven't seen reasoning data. So do you know, by the way, before we kind of end up, I think this is really important. Why did they call it Strawberry? What's the Strawberry problem?
I have no idea. What is the Strawberry problem?
So the reason why they call it Strawberry, so it's you can ask an LLM how many R's are in strawberry, and it's going to give you very different answers, right?
It's 3, right? 3, right?
It is 3. Yeah. But the way that it sees the data, it says that strawberry is usually 2 tokens, right? It's straw
and a berry.
And then berry. So it sees it as 2 different tokens. So when you ask it, like, it doesn't really understand. It doesn't count letters. It doesn't reason that he has to count the letters, break it up and count the letters. Interesting. Like, it doesn't reason that way. It just sees it based on tokens. And based on tokens, it's like, oh, there's two R's in there, or because it sees the RR and then it says, so what is learned from other things. So it's not really counting the R's. It's like inferring certain things based on training data sets. So that there's no reasoning there. So that's the Strawberry problem, right? So, you can ask a system how many R's are in strawberry, and then it will tell you, and then that's how you figure out, oh, there's some reasoning happening behind it, and that's why they call it Strawberry. So I think we'll leave it at that, but the part that's really important here is that this is fascinating. I really, really kind of like the idea of, like, how do we move from just token-based systems to now having data that is, step-by-step data, reasoning data, that we can give it a problem and it can reason through and give us an answer at the end. And usually that answer is a lot better than, giving us a pattern of what it has seen, what it thinks, right?
And no doubt, that's the future. That's where we're going. And creating, the layers of how do I do this with next generation architecture, specifically how do you apply these transformers, how do you keep on building these ideas of ethics and regulation, AI governance is going to become fundamental. All those things will come in play. But Ardis, in a way, to this conversation takes a step back from the future and reminds us that AI as the discipline has been around. And in terms of reasoning, these 3 principles are trying to mimic human-like behavior, in which we kind of use deductive, inductive, abductive, or in ideas common sense. So how computational machinery will go through those stages. So I hope everybody kind of gets a sense of how it could look like, and particularly how systems could be programmed to do that. And as I said before, the good and the bad, and what is needed to accomplish that. Ardis, do you want to sign this off?
Well, this is great. Until next time, everybody. Generation AI is part of the Enrollify podcast network. If you like this podcast, chances are you're going to like other Enrollify shows too. Our podcast network is growing weekly, and we've got a wide range of marketing, enrollment, and higher ed technology shows that are jam-packed with stories, ideas, and frameworks, all designed to empower you to be a better higher ed professional. Our shows help higher ed leaders and professionals like you find their next big idea. They feature a selection of the industry's best as your hosts, like Jamie Hunt, Seth Odell, Jenny Lee Fowler, Brian Gross, and many of your favorite leaders in higher ed. Enrollify is made possible by Element 451, the next generation AI student engagement platform that's helping institutions all over the country create meaningful, personalized, and engaging connections with their prospects and students. Learn more at element451.com.